So this is our last video lecture in the Bayesian machine learning course. And in this lecture, we will provide a summary of what we've covered during the semester. There is also a notes document that goes with this summary, and it has considerably more information in it than we'll cover in this video lecture. So make sure you take a look at it. It's a good way to find information from the semester topics that we covered that'll be useful for the quiz, and it's also useful for you as a professional going forward as a place to go back when you want to look up something really quickly and find where it was. It's a good place to go to find that quick summary. So when we began the course, we looked at the title, Bayesian Machine Learning, and we looked at its components, and we talked about each of those components. And we looked first at machine learning and said that machine learning uses data to improve automatic responses. It takes data in and it generates responses out that help people solve problems. It has demonstrated its applicability across a wide range of areas. Bayesian methods are rigorous mathematical techniques that have foundations in probability theory, and they have demonstrated their ability to manage uncertainty in a variety of contexts. So Bayesian machine learning then can help us to explicitly account for the uncertainty present in most machine learning problems. And this means that it will extend the applicability of machine learning problems through a wide range of domains, and it will help us solve more complex and important problems than we could before. So our course goals were to provide an understanding of uncertainty management, this key part of what probabilistic reasoning brings to machine learning. We were also interested in developing skills in probabilistic modeling. Probabilistic thinking is not something that comes as part of our intuition. We need to develop it. And the work in this course was designed to provide an opportunity to develop that intuition in probabilistic thinking. And finally, to provide a foundation for lifelong learning. A lot of the basic programming that we did in this class is using methods that frankly are going to change quickly. They've changed in the last few years, and they'll continue to change rapidly as we learn more about how to implement these techniques in more efficient and effective ways. So the first major topic we looked at in the course was a probability review. And we started with the axioms of probability and showed how they define this function that gives us a measure of uncertainty. And then we showed two important rules from these axioms, the sum rule and the product rule. And these rules are the foundation for building most of the reasoning that we use in probabilistic thinking. We then described the definition of conditional probability, and from that, of course, we developed Bayes' rule. We also described random variables, probability distributions, both discrete and continuous, univariate, multivariate. And then we talked about moments, in two particular moments. The first moment, which is known as the mean, and the second moment about the mean, which is known as the variance. And finally, we spent a bit of time talking about this notion of conditioning, which is really an extension of the sum rule. And we said over and over again throughout the course that this is how we can solve problems. That if we're given a distribution that we need to either parameterize, we need to find the most likely parameters for it in a Bayesian sense, or we need to sample from it or represent it in some way, that often it's more convenient to condition on another variable and then to use the sum rule to basically sum over or integrate over all possible values of that variable in order to discover the target distribution or the target expectation that we're looking for. In the Bayesian modeling and analysis part of the course, we began by looking at priors, this very important part of Bayesian analysis, and the different ways that you can obtain prior distributions. You can use the most useful way to get them is to use base case information, the baseline information that's available in any area. So in other words, if you're thinking about, for instance, a disease, it's the number of people in the total population with that disease. So you're looking for these base level prior distributions that can be used in Bayesian analysis. But then we spent quite a bit of time talking about the conjugate approach, which is a convenient way to get a closed-form analytical solution, and it gives really fast answers. Conjugates represent a good way to think about problems because we know what the answer should be, and we can always do comparisons against that answer. We also talked about non-informative priors and how that really is the basis for all of maximum likelihood or frequentist ways of doing probability. And when we really come into a problem with no information, going with a non-informative prior makes some sense. We then looked at statistical decision theory and defined what it means to be Bayes optimal. And to be Bayes optimal, you basically are looking at solutions that minimize the expected loss. So among all possible choices, which is the one that minimizes the expected loss function for that problem? And then we defined Bayesian classifiers, and we showed that there were optimal classifiers that we could find that would always give us the Bayes optimal solution. But these classifiers had fairly stiff restrictions, one of which is we really had to know the underlying distributions. And we gave examples that are used in practice that are based upon Gaussian assumptions for those underlying distributions. And those are called quadratic discriminants and linear discriminants. And those work well over certain classes of problems. We then looked at an approach to Bayesian classification called naive Bayes that relaxes the assumptions regarding the codependence of variables and says that all these variables in our data are independent. And it turns out this approach is very effective across a wide variety of problems, including text analysis and text mining. Finally, in our Bayesian modeling and analysis module, we looked at Bayesian regression. And optimal Bayesian regression turns out to be ridge regression and lasso regression, depending upon the loss function that we use. So these derive naturally from a Bayesian formulation. Now, unfortunately, many problems are way too complicated to solve for closed-form solutions. The simple ideas of using conjugate priors don't work for many real-world problems, for instance. And we need to solve these very complex problems. And typically it requires things like solving for the integral of the summation that's in the denominator of Bayes' rule, or finding likelihoods. And this turns out to be very difficult to do, particularly for problems in which there's a chaining or a hierarchical relationship between prior distributions and between likelihood functions. So the result is that we need to use sampling methods or some other approximation method. And sampling methods are one of the two approaches that we talked about in the course, the other being variational approximation for going after these complex problems. Sampling methods are the older of the two. To start the notion of how we build sampling methods, we talked about Markov chains, and we gave the fundamental principles of Markov chains. The idea extending conditional probability, in particular extending the notion of independence to the notions of conditional probability, but conditioning only on the previous event, the previous occurrence. So if we've got a chain of random variables, a random variable is only dependent upon the previous random variable in that chain and not on any other random variables that occurred before it. So Markov chains are a very powerful way for us to model problems where there's some conditioning. To motivate the use of Markov chains for sampling, we talked about Monte Carlo sampling, and in particular rejection sampling, which use independent samples in order to build an approximation for distributions. The problem with methods like rejection sampling, however, is that they don't scale. They don't scale to large data problems, and they don't scale to multidimensional problems. And so we really need something else. And the idea then of going to Markov chains as a sampling method is something that people thought of in the 40s, and it turns out that it has applicability to Bayesian analysis, which people thought about in the 1980s. And this is where the notion of Markov chain Monte Carlo comes from. It comes from the idea that instead of doing independent sampling, we do sampling according to a Markov chain. And this sampling according to Markov chain gives us very accurate estimations for distributions and expectations than we could get with independent sampling. And most importantly, using the Gibbs implementation of Markov chain Monte Carlo, we can go to multidimensional problems. So we can actually solve real problems with MCMC that we can't solve with traditional Monte Carlo sampling. Today, there are extensions to the basic MCMC that work even faster than the original MCMC implemented in the 80s, extended through the 2000s. But in the last 5 to 10 years, there have been major extensions to MCMC to make it faster. Most notably, Hamiltonian Monte Carlo, which uses the gradient in order to get us quicker solutions than we can get with just basic MCMC sampling. The next approach to approximating distributions and expectations is called variational approximation. And this is the most modern of the approaches. And we motivated the idea of variational approximation by first talking about mixture models. And mixture models are a way to combine distributions using a weighting, a probabilistic weighting of those models. And the example we gave was a mixture of Gaussians that could be used to represent an unsupervised learning problem where we've got a lot of data, we think it's structured, but we don't know the structure. And mixture models provide us a way to do that. For instance, we could think of the structure as being a mixture of Gaussians. And we showed that this notion makes sense for unsupervised learning problems, but that we need a way to get an answer to those mixture modeling problems, and that way to get the answer is called expectation maximization. And the EM algorithm is a very effective way for us to find the solutions to these mixture model problems. And in general, the EM algorithm serves as the basis for approximations, and in particular for variational approximations to distributions. So we can use the EM algorithm as the basis to building these approximations. This variational approximation technique then is built on the notion of optimization. It's not built on the notion of classical inference where we're trying to estimate a density function using sampling methods. It's based on the notion of doing an optimization. In this case, the optimization is minimizing the Kullback-Leibler discriminator or maximizing the elbow or the evidence lower bound. These optimizations then give us close fits to unknown distributions. They're not as close a fit as we get with MCMC, but in many problems they're good enough. And the difference between this approach and MCMC is this approach scales to really big data problems. So unlike MCMC, which can only be used for moderately sized data problems, variational approximation can be used for the truly big data problems that we face today in data science. And this variational optimization approach then has been implemented in a number of packages. What's different in going on, the ongoing thing that's happening in variational approximation and variational optimization is that up until a few years ago, in order to use this approach, you had to write your own optimization routine. But now people are writing packages that allow us to come to the problem with just a probabilistic formulation and use a given optimization routine, like the ADB approach, which you can basically just describe the problem that you have probabilistically, and it will use variational optimization to give you an approximation to the fit that you want. We also looked at graphical methods for Bayesian machine learning in the course, and it was split into two parts, one toward the beginning and one toward the end. And toward the beginning, we talked about the notion of Bayes nets, this idea of networks of nodes, and that is, networks of nodes then can be used to represent joint probabilities because the arcs in those networks were directional arcs showing conditional probabilities. And so that product of conditional probabilities in the arcs gave us these joint distributions that we were interested in. And these Bayesian networks, their underlying assumption with those directional nodes is there's some sort of causality there at work. We showed how these techniques could be used for Bayesian regression, and we also showed how they could be used for generative models. And in generative models like latent Dirichlet allocation, they describe the underlying causal structure for the creation of words or documents and the words in those documents. We also showed how graphical methods could be used to visualize modeling. And this is an important concept. It's a way for us to connect the mathematics of Bayesian probabilistic inference with a real problem that we're dealing with. So these graphical visual models are very powerful in that sense. They communicate what we're trying to do probabilistically as it relates to the problem at hand. Finally, we talked about Markov random fields in our last module of the course. And Markov random fields represent an undirected set of arcs in a network or graph as opposed to directed sets. So there's no notion of causality. There's a notion of relationships. And this notion of relationships has a lot of applications in image processing, in bioinformatics, and in other areas. It's a very useful technique. And we showed that one example of this is a basic technique from deep learning and from neural nets known as the Boltzmann machine, which is a good example of a Markov random field. And these Boltzmann machines and restricted Boltzmann machines can be used to give us estimates of distributions. And as such, they can help us find, for instance, changes to those distributions that may exist in problems like fraud detection. Finally, we talked about hidden Markov models. And hidden Markov models are a kind of a clever way to put together both the notions from Bayes nets with the notions from Markov chains to represent problem spaces. And they represent cases where there's some unknown latent variable that is in fact causal to some visual information that we're seeing. For instance, the state of a company. If we're interested in financial matters and investing, the true state of a company we can't know, but we can know things like the visible price at which its stock sells for. So we know those kind of things. We're getting a signal, but we don't know exactly what the hidden state is. And those kind of problems are well described by hidden Markov models. These are problems that are dynamic. They change. Something is changing over time. So the state of that company is changing over time, and we see this visible signal that's coming, and we want to estimate the unknown state represented in this hidden Markov model. All right, so we've covered a lot of stuff in this course. It's given you a lot of background in how you can model uncertainty using probabilistic techniques. And as such, these kinds of techniques are applicable to a lot of machine learning problems. They're applicable to unsupervised learning problems, and we see that in new methods like variational autoencoders. It's applicable to natural language processing and topic models, as we saw in the course. It's applicable to temporal and spatial models. We saw that this temporal application with these hidden Markov models and things like that, and spatial models as well. It's applicable to image processing, Boltzmann machines. It's applicable to deep learning and neural nets. You've learned a lot. There's a lot of stuff that you've covered, but there's a lot you need to learn. And the good thing about it is the background that you've had in this course and all these topics, these different topics, will serve you well as you try and learn new things and apply what you've learned to new problem spaces. So I wish you the best of luck as you go forward in your careers as data scientists, and I hope that you will continue to learn not only about probabilistic modeling, but also about the fun and exciting field of data science. Best of luck to you in your careers.